Hello everyone, welcome back to my channel. Today I'm going to discuss about the contribution of the HOMO and LUMO for the electrophilic substitution reaction. Like for a reaction, how can you decide that reaction will happen or not for the electrophilic substitution? So if you can check their HOMO orbital or LUMO orbital, then you can get some idea. So I will discuss 4 different reactions today, which I predicted that reaction is going to happen based on the HOMO structure, like electron density in the HOMO of that molecule. So first, let's see what is HOMO and what is LUMO. So any atom, when another atom comes together to make a bond, they form the molecular orbital. So atomic orbital combine together, and 2 orbital combine, making 2 different orbital. One is HOMO, another is LUMO. HOMO means highest occupied molecular orbital. So suppose those atomic orbital has an electron each. So 2 electrons. So those 2 electrons will go opposite spin in the lowest energy molecular orbital. And that's why, since that is occupied with the electron, that's why occupied. And highest means energetically highest. And that's why highest occupied molecular orbital. But LUMO is lowest unoccupied molecular orbital. Lowest means energetically low, but unoccupied means there is no electron. So that's why it is called LUMO, L-U-M-O. You will understand if I explain that HOMO and LUMO with the butadiene molecule, then you can predict like which is HOMO and which is LUMO. Let's see how they are forming HOMO and LUMO. So in butadiene, there are 4 carbon center, 1, 2, 3, 4. So let's draw 4 carbon, 1, 2, 3, 4. The number of center is number of wave function. So you can say this is one wave function, psi 1, and there is another carbon, so it should be psi 2, another carbon, there will be psi 3, and there is another cycle, there will be psi 4. So since it has a double bond and it has a double bond, these are conjugated, so it should have definitely the p orbital, unhybridized p orbital. Okay, and each double bond has 2 electrons. So make energy state like 1, 2, 3, and 4. So those 2 electrons. Now first look for the same phase. So those orbital will have like same phase, all of them. There is no nodal point. What is nodal point? You can find out this nodal point by this. So nodal point is n minus 1. So if it is 1, so 1 minus 1 equal to 0. So the first wave function, there is no nodal point. That means all are same phase, same side. So in that case, no nodal point. And so ultimately you can draw this carbon. So all are the same, so you can draw all together like this. Okay, now let's go to the second one. It has 2. 2 means 2 minus 1, 1. So it will be 1 nodal point that should be in the middle. Like you can make a wave like this. You can separate these like this. So these 2 will be same phase, and then these 2 will be the same phase. So in that case, you can draw like this. And this. So this is another wave function. And then for the third one, 3 minus 1, there will be 2 nodal points. So you can find first one nodal point here, another nodal point here. So you can make a wave like this, go like this. So this will be, and these two will be same, and that will be like shaded. So in that case, you can draw like this. Now the fourth one, I'm erasing this molecule. So fourth one, 4 minus 1, like 3, there will be 3 nodal points. So 1, 2, 3. So ultimately, all of them will be like this, like same wave, like same phase. Like, so if it is like this, so it will be like this, and it will be like this, and it will be like this. So in that case, you will get like this, alternative, same thing. And so in that case, originally the butadiene, as I mentioned before, they are conjugated, but they have 2 double bonds. So each double bond contain 2 electrons. So 2 double bond contain 4 electrons. So according to above principle, first one pair of electron will go down. Oh, remember another thing, energetically, this is energetically higher. Yeah, if you go, and these are energetically lower. So first electron will go to the lowest one, then remaining 2 electrons go there, and there is no more electron remaining. So now there are 2 occupied orbital. Now find out which one is occupied and energetically higher. This one. That's why it is called HOMO. Okay? This is HOMO of the butadiene. So energetically higher, that's why H, highest. Okay? Highest occupied doesn't mean that like it will be occupied by all 4 electrons. No. Highest means energetically higher. Occupied, O means occupied, highest energetically. Occupied means by electron, molecular orbital. Similarly, now there are 2 unoccupied orbital, or like energetically state. So since we are saying like energetically higher here, so among these 2, which one is energetically lowest? This one. So that's why it is called LUMO, means energetically lowest, and there is no electron, that's why unoccupied molecular orbital. So lowest unoccupied molecular orbital. So these 2, like HOMO and LUMO, one is occupied with the electron, another is empty with the electron. So these 2 are called HOMO and LUMO, and they are frontier. They are also called together frontier orbital. And for reaction, these HOMO-LUMO really contribute a lot, especially also for the UV transition. That frontier orbital has a contribution, like real contribution for the electron transition to get the UV absorption, and many other spectroscopic technique also depends on the HOMO and LUMO. So frontier orbital is always important to consider. So now today in my discussion, I will also show how HOMO can direct you to decide whether your reaction will happen or not. So now I'm going to show you 4 different reactions which you can get a clear idea how HOMO is contributing for the electrophilic substitution reaction. Let's see those reactions one by one. Okay, number 1 reaction. I want to make this molecule, and definitely I can make this molecule from here. If I have carboxylic acid group here and if I have aryl group here, so easily I can use sulfuric acid, concentrated sulfuric acid, and it will cyclize these to make this 5-membered ring with the ketone. So, and to make this compound, what I need dibromo of this compound with the carboxylic acid. And I can do the Suzuki coupling reaction here with the aryl boronic acid. So if I use boronic acid, palladium couple, Suzuki coupling, so I will get this compound. Condition is you can just take this compound, aryl boronic acid, and like palladium tetrakis, triphenyl phosphine, and sodium carbonate solution in water. So, and the solvent should be like DME, like 1,2-dimethoxyethane, or in short DME, and then reflux it, you will get this product. I made this product therefore by this way. If you have any question about this reaction, ask me in the comment section. I will give you the answer how you can do this reaction. So now the point is, the aryl boronic acid is easy, commercially available to buy, and catalyst and DME, those are available. But now we need this compound, and from where we can get this compound, we can make this compound dibromo dimethyl. You can oxidize this methyl group with the potassium permanganate in 1:1 t-butanol and water mixture. Add the potassium permanganate and this compound 1:1 t-butanol and water. Again, if you need any help for this oxidation, ask me in the comment section. I can show you what is the procedure or like how can you make it. So this compound, like you can oxidize with the potassium permanganate, KMnO4, to carboxylic acid, dicarboxylic acid. This both methyl group will be oxidized. Now the point is this dibromo compound. So how can I make this dibromo compound? So if I take metaxylene compound, dimethyl benzene, and if I want to do the bromination, Br2, and little bit iodine catalyst, very small amount iodine catalyst, okay, and the solvent. So you can find the dibromo here. Point is, in this benzene, the 3 point where you can get bromo here, not 3 point actually, 4 point here. There are 4 position. If you do add the bromine, then you might get the brominated those position also. So this is the like crucial point for that HOMO direction, like HOMO picture. Like if you see the HOMO orbital, then you can say, okay, this compound will give only this dibromo, not these 2 position. Why? Because electron density of the HOMO molecule. So let's see how it looks like. Okay, let's see the reaction 1. Here I was talking about the xylene bromination, so it happened only these 2 position. So if we take this 1, 2, 3, 4, 5, 6, so 2 and 4 position bromination happen. So if you look on the HOMO molecule of this xylene, you'll see the electron density is here and here, and they're also there, but those two position is occupied by methyl, so there is no substitution will be happening. So with the bromine addition, bromine will go only these two position, but other two position like uh, 1 2 3 3 and 6, 3 and 6 position doesn't have any electron density. These two position is called nodal point. So in the nodal point, the electrophilic substitution will not happen. So that's why you are getting dibromo compound from this molecule. Now the case number 2, second types of reaction, that is also I decided to move on by observing their HOMO orbital, like seeing their electron density in the HOMO molecule, and that reaction will further go or not. Let's see what is that molecule looks like, and what is the reaction. So this is the fluorine molecule, alkylated dialkylated fluorine molecule. So our target was to add the Friedel-Crafts acylation reaction here. So we used 2-bromobenzoyl chloride, having bromo here, 2-bromo, okay, and same case here. So that reaction R can be methyl or hexyl. That reaction actually happened here like this, the bromo, and also this side bromo. And since you have the bromo here and there is a proton actually, so this is also has a proton, so palladium catalyzed reaction give cyclization with this H and bromine, thus it form a cyclic compound. So let's see how it looks like. So it was like this. So this molecule, and after that this molecule, this 2-carbonyl was reduced to this CH2 here, and after that alkylated again. And I'll give you a paper reference to see this molecule synthesis, total every procedure, everything in detail. So once it was like 2 phenyl ring, so that reaction happened. Now it is 4, 1 2 3 4. So there are 4 thing, and we want to extend this molecule by doing the same reaction, like this Friedel-Crafts acylation, to make like 6 of them. Like now 1 2 3 4 phenyl ring, then we wanted to make 6. So yeah, finally we have seen this HOMO orbital, and we could decide, yes, this reaction will happen because of the HOMO electron density in the HOMO, like this side, okay, like more electron density there. I'll show you the picture, or like those HOMO orbital. So finally we could do like 6 of them, like same. I'm not drawing the molecule. If you are interested to see that molecules and paper, you can see the link. I'll show you just a couple of minutes later. So finally we make like 6 of them, so I can say P6. And still after P6 we wanted to see whether it will go further extension or not. Still by seeing the HOMO, we have seen the P6 could be converted to P8. Like P6 also had some electron density in their HOMO in the end of this molecule, and finally we made the P8. But interestingly, after P8 we have seen the homomolecular orbital, like HOMO of this P8, and it was showing there is no electron at the end, and after that we couldn't make like more than that, like a more extension. So you now let's see how the HOMO orbital of those molecules and how we decided to do that reaction. Now reaction 2. So this reaction, you will find this paper. This is published in Organic Frontier Chemistry. This is the link, like the paper you can find. So let's see the reaction. So here this molecule is like fluorine molecule. So this HOMO of this molecule is this. So electron density is mostly dense here. So if I do Friedel-Crafts acylation, it happen two equivalent. So two equivalent of this. So it happen here, and after making this, after cyclization and the reduction, then after alkylation, we got like four phenyl ring here, and after that, this once we made this four, so we checked the HOMO density also again for this molecule. So you see the electron density is here also available. So this reaction also occurred like to make six phenylene. So it happened in both sides. And once we made the six, then again we checked the HOMO of this, and you can see electron density is decreasing, but still electron density is there. So to make 8 phenylene of this, we did this reaction and it happened, like we made this diacylation of the 6. But once we made the 8 after cyclization and reduction, and then we tried to make 2 more phenyl ring addition, but it didn't happen, like we didn't get any product. So if you see the HOMO density of that 8 molecule, there is like almost nothing there. So like we couldn't make the 10 phenylene compound from the 8. So here you can clearly see how HOMO picture is giving you the electron density indication, like whether reaction will move forward, like will happen or not. Number 3 reaction, which I am going to talk now. So if we consider the fluorine molecule again, this is fluorine molecule R. So for electrophilic substitution reaction in this molecule, like these both positions are vulnerable, like active. So it can happen in both these two positions, also these two positions, but not these two. Why not? You will understand. Why not? You already have understand. Those are the nodal point of this benzene ring. So nodal point doesn't have any electron density, so the electrophilic substitution will not occur these two positions. But other two positions are kind of active. So based on different condition, you can do functionalization of this molecule. Now, I want to make a molecule, similar molecule, this molecule where I want to connect a aryl group here, and also I want iodo group here. So how I'm going to make this molecule? So in that case, first I will make amine in that position, and then I'll put something here. So if you do the bromination after putting the amine, so ortho position to the amine group, like in that case these both two position could be active for the bromination. So and I don't want to put the bromine here, and iodination is not easy, so only one position you can make, if you can put here the nitro group, and keeping this nitro group, you can make the diazotization to make the bromine here. And once you get the bromine, then just use the boronic acid with phenyl ring. So it will be connected. And once you get that molecule, then reduce this nitro to amine. And then again diazotization, you can make iodo compound. Now, once you have the amine group here, nitration is not easy like only this selective position. But if you do something here, if you protect amine group here, and if you do acetic anhydride reaction, okay, in the condition, I can give you the condition if you want, but there is a way to do, like to put the acetate group here. So in that amine group, one acetate group is attached here. So once you form these, then you can calculate the HOMO density or HOMO orbital of this. Then it looks like these positions are like kind of less electron density, and selectively if you do the nitration, like nitric acid reaction, nitric acid nitration, so nitro group only going to this position, not that position or that position, only this position. Once you are this like protected with the acetate group, so NH acetate group, so in that case nitration reaction give you the only nitro group here. And once you get this, then you can deprotect this acetate group here, then you can convert it NH2, then you can convert the NH2 to the iodo easily, while iodo or bromo, iodo is more fine. Then you can keep the nitro, don't reduce it. Once it is iodo, then do the Suzuki coupling, attach whatever the functional group you want, and you can keep the nitro group here. And then nitro group, once you attached is done, then you reduce your nitro group to amine, and amine to iodo or bromo again. That is easy. But that is interesting. While this molecule HOMO orbital is kind of different of these HOMO orbital, like while nitration is not done yet, like your acetate group is there. So this HOMO orbital, I'll show you the picture difference of these two HOMO orbital of this molecule, so you'll understand why the nitration is happening only this position, not the other positions. Let's see what it looks like. Let's see reaction 3. So here, if you take the fluorine molecule, both side has the electron density almost similar fashion, and we wanted to make like nitro product here. So if you see here, nitro group, addition of nitro group here by doing the nitration using fuming nitric acid in acetic acid, room temperature 30 minutes. So just to put nitro group here. So if you see the acyl amine fluorine molecule, so you see that like most electron density is here, like this position, and this position is less and also a little bit less. You can ask like why it is not happening. So there is primary indication that for the maybe for the smaller reaction time, the nitration happen only in this position, although it has some electron, so probably there's something else too. But this is a good indication if you see like the only HOMO molecule of the fluorine and versus the NHAC, so it is happening selectively in this position. So clearly there is a difference in the HOMO picture. The fourth molecule, let's draw first. This molecule is called dibenzopricin, and if you do a functionalization here, Now you can remember here like single bond. So if you do the Scholl reaction, like electronic reaction here, like in presence of acid or Lewis acid, so it will cyclize here only to make the kind of is a helical compound. So it will be cyclized here, but since this thing can rotate, so whole thing can rotate if you protect here like with the T-butyl group, so the whole thing can rotate. If it is rotated, then you can also think this molecule, once it is rotated there with the single bond, so it could be like this. If it is rotated, so again it can also cyclize this position. So my point to say this position or this position, which one it will cyclize. So when we did this kind of reaction, I will show you the paper reference, you can see if you are interested. So in that case, Scholl reaction happen only like cyclization only in this position, like when it was like there. So it happened only this position, not that position, like it didn't rotate or like make this. Why? Because again, if you look its HOMO orbital, then you will see the electron density is there and there, not there, not there. So these two are nodal point. So in nodal, due to be nodal point, it didn't happen. And how we prove that that reaction didn't give the other part? Because we made the other compound individually in another different reaction to confirm that was not present in their crude, and like we couldn't get, or we couldn't detect any of that molecule. So let's see how that molecule looks like and how we decided like how HOMO is indicating you, yes, this reaction will not happening in that position. So there are total 4 reactions I'm talking about. There are many other reactions you can maybe think how whether that reaction will happen or not depending on their HOMO density. Now let's see reaction number 4. It is interesting. So this reaction you will find in this paper published in Organic Letter 2021-23 volume and 5170 paper page number. So if you're interested to see this paper, you can go to this paper and can see the reaction and the story, what we made and how it happened. So the interesting things, these molecules also, so like you can decide on the like HOMO density. So these are connected with a single bond here. So this single bond can rotate to come here to cyclize, but it didn't happen. Rather, it made more steric hindered like helicine compound. So if you see the like precursor HOMO orbital, so even if it can rotate there, it cannot cyclize here because this is a nodal point, no electron density there. But here is the electron density, and also for here the electron density, so cyclization can happen here. This is not electrophilic, really electrophilic substitution, or maybe it is a Scholl reaction, but still it is also occurring based on the electron density availability of the carbon. So these two isomer were the product from these, and some other example also here. So we also try to make that same compound from this tetraphenyl ethylene core. So we have found it once it produce couple of side like so the HOMO of this molecule is this. So if it cyclize one side, then you can see the HOMO density or electron density move to one side, not other side, and that's why this reaction never finished to give this helicine type compound, because HOMO density shift one side. Like if you see, suppose one side helicine is formed by some reason, so you can see the HOMO density again like totally shifted to one side. That is called HOMO disposition, like HOMO is completely positioned to one side and other side is totally empty, so cyclization didn't occur here because of the electron density.